Hello everyone. A circle is a set of all points equidistant from a given point. So today let us discuss something more related to this in our lesson circles. Circle. The collection of all points in a plane which are at a fixed distance from a fixed point in the plane is called a circle. The line segment joining the center and any point on the circle is called the radius of the circle. Diameter is 2 times the radius. The fixed point is called the center of the circle. If we take 2 points P and Q on a circle, then the line segment PQ is called a chord of the circle. A piece of a circle between 2 points is called an arc. The region between an arc and the 2 radii joining the center to the end points of the arc is called a sector. Angle subtended by a chord at a point. We take a line segment PQ and a point R not on the line containing PQ. Join PR and QR. Then angle PRQ is called the angle subtended by the line segment PQ at the point R. Angle POQ is the angle subtended by the chord PQ at the center O. Angle PRQ and angle PSQ are respectively the angles subtended by PQ at points R and S on the major and minor arcs PQ. Theorem 1. To prove equal chords of a circle subtend equal angles at the center. Proof. We are given two equal chords AB and CD of a circle with center O. We want to prove that angle AOB is equal to angle COD. In triangles AOB and COD, OA is equal to OC, radii of a circle. OB is equal to OD, radii of a circle. AB is equal to CD is given. Therefore, triangle AOB is congruent to triangle COD by SSS rule. This gives angle AOB is equal to angle COD by CPCT. Theorem 2. If the angles subtended by the chords of a circle at the center are equal, then the chords are equal. Theorem 2 is converse of the theorem 1. Perpendicular from the center to a chord. Let there be a circle with O as center and let A be one of its chord. Draw a perpendicular through O cutting AB at M. Then angle OMA is equal to angle OMB is equal to 90 degree or OM is perpendicular to AB. We conclude that the perpendicular from the center of a circle to a chord bisects the chord. Theorem 3. To prove the line drawn through the center of a circle to bisect a chord is perpendicular to the chord. Proof. Let AB be a chord of a circle with center O and O is joined to the midpoint M of AB. We have to prove that OM is perpendicular to AB. Join OA and OB. In triangles OAM and OBM, OA is equal to OB, that is given. AM is equal to BM, given. OM is equal to OM is common. Therefore, triangle OAM is congruent to triangle OBM, that is by SSS congruent rule. This gives angle OMA is equal to angle OMB is equal to 90 degree by CPCT. Circle through 3 points. Infinite number of circles can be drawn through 1 or 2 points. In case there are 3 collinear points, then circle can be drawn, but the third point will lie outside the circle. Let us take 3 points A, B and C which are not on the same line. Draw perpendicular bisectors of AB and BC, PQ and RS respectively. Let these perpendicular bisectors intersect at one point that is O. Conclusion. O lies on the perpendicular bisector PQ of AB. We have OA is equal to OB. Similarly, as O lies on the perpendicular bisector RS of BC, we get OB is equal to OC. So, OA is equal to OB is equal to OC, which means that the points A, B and C are at equal distances from the point O. We conclude that there is one and only one circle passing through three given non-collinear points. Equal chords and their distances from the center. Let AB be a line and P be a point. Since there are infinite numbers of points on a line, if we join these points to P, we will get infinitely many line segments PL1, PL2, PM, PL3, PL4, etc. Out of these line segments, the perpendicular from P to AB, namely PM, will be the least. We conclude that the length of the perpendicular from a point to a line is the distance of the line from the point. Theorem 4. To prove equal chords of a circle are equidistant from the center. Proof. Take a circle of any radius, draw two equal chords AB and CD of it and also the perpendiculars OM and ON on them from the center O. Divide the figure into two so that D falls on B and C falls on A. We observe that O lies on the crease and N falls on M. Therefore, OM is equal to ON. Theorem 5. Chords equidistant from the center of a circle are equal in length. Theorem 5 is converse of the Theorem 4. Angle subtended by an arc of a circle. The endpoints of a chord other than diameter of a circle cuts it into two arcs, one major and other minor. If we take two equal chords, they are more than just equal in length. They are congruent in the sense if one arc is put on the other without bending or twisting, one superimposes the other completely. We can verify this fact by cutting the arc corresponding to the chord CD from the circle along CD and put it on the corresponding arc made by equal chord AB. We will find that the arc CD superimposes the arc AB completely. This shows that equal chords make congruent arcs and conversely congruent arcs make equal chords of a circle. We conclude that if two chords of a circle are equal, then their corresponding arcs are congruent, and conversely, if two arcs are congruent, then their corresponding chords are equal. The angle subtended by an arc at the center is defined to be angle subtended by the corresponding chord at the center in the sense that the minor arc subtends the angle and the major arc subtends the reflex angle. The angle subtended by the minor arc PQ at O is angle POQ, and the angle subtended by the major arc PQ at O is reflex angle POQ. We conclude that the congruent arcs of a circle subtend equal angles at the center. Theorem 6. To prove the angle subtended by an arc at the center is double the angle subtended by it at any point on the remaining part of the circle. Proof. Give an arc PQ of a circle subtending angles POQ at the center O and PAQ at point A on the remaining part of the circle. Consider the three different cases arc. PQ is a minor arc, PQ is semicircle, and in arc PQ is major. Let us begin by joining AO and extending it to a point B. In all the cases, angle BOQ is equal to angle OAQ plus angle AQO, because an exterior angle of a triangle is equal to the sum of the two interior opposite angles. In triangle OAQ, OA is equal to OQ, that is the radii of a circle. Therefore, angle OAQ is equal to angle OQA. This gives angle BOQ is equal to angle OAQ. That is equation 1. Similarly, angle BOP is equal to angle OAP. Equation 2. From 1 and 2, angle BOP plus angle BOQ is equal to 2 multiplied by, in the bracket, angle OAP plus angle OAQ. This is the same as angle POQ is equal to angle PAQ. From the case where PQ is the major arc, 3, it is replaced by reflex angle POQ is equal to angle PAQ. Theorem 7. To prove angles in the same segment of a circle are equal. Proof. According to the Theorem 6, angle PAQ is equal to half of angle POQ is equal to half multiplied by 180 degree is equal to 90 degree. If we take any other point C on the semicircle, again we get that angle PCQ is equal to 90 degrees. Suppose we join points P and Q and form a chord PQ in the figures used in the Theorem 6. Then angle PAQ is also called the angle formed in the segment PAQP. A can be any point on the remaining part of the circle. So if we take any other point C on the remaining part of the circle, angle POQ is equal to angle PCQ is equal to angle PAQ, which are both 2. Therefore, angle PCQ is equal to angle PAQ. Theorem 8. If a line segment joining 2 points subtends equal angles at 2 other points lying on the same side of the line containing the line segment, the 4 points lie on a circle. That is, they are concyclic. Theorem 8 is converse of the Theorem 7. Cyclic quadrilaterals. A quadrilateral ABCD is called cyclic if all the 4 vertices of it lie on a circle. If we observe this cyclic quadrilateral, we find that angle A plus angle C is equal to 180 degree and angle B plus angle D is equal to 180 degrees. Neglecting the error in measurements, we conclude that the sum of either pair of opposite angles of a cyclic quadrilateral is 180 degree. In converse of this, we conclude that if sum of a pair of opposite angles of a quadrilateral is 180 degree, the quadrilateral is cyclic. So this was all about our lesson circles. A circle encloses the maximum area for a given perimeter. So they can be used in various applications in our daily life. So knowing about this is very important. Thank you, students.